So we have a infinitely long wire here. Whenever we hear the word long, it always means that we have an infinitely long wire. If we have an infinitely long wire, this is the formula we use for its magnetic field. Now then, the idea is to find we have the wire and we have the loop, and the idea is to find the net force on the loop, knowing that the current in I1 is equal to 5 amperes and the current in the loop, or I2, is 1 amperes. Now we kind of need to use, I already told you about this formula, we'll need to use it in this problem, and the other formula is this one. This formula represents the force on the loop by the magnetic field of the first wire of this wire. The first thing we need to do is apply the right-hand rule, specifically on this wire. So our thumb is going to point upwards, it's going to point in the direction of the I1. And we're going to curl our hands around, basically if you're sitting and you have your tablet in front of you on the table, your thumb is going to point sort of in the J-hat direction, parallel to your table, and you're going to curl sort of in the K direction, just going to go into the table and out of the table. So as you curl your fingers, we're going to kind of go like this, in this direction. Now, when we're going to specifically focus on this point here of the loop. What I'm trying to do is find the force on each segment of the loop. I'm breaking the loop down into 4 smaller wires, and I'm trying to find the magnetic field of the first wire on each of these segments. So I apply the right-hand rule to figure out the magnetic field of wire 1 at this point on this wire. When I do that, I curl my fingers, point my thumb towards I1. I realize that here, along this wire, the magnetic field is always pointing into the table. If your tablet is flat on the table, your magnetic field is going to point into the table. Basically, this segment of the loop is sort of on the right-hand side of this wire of I1. So, anywhere along this segment of the loop, the magnetic field of B1 points in. I'll do the same for the other segments, and then I'll get to the solving because it's going to make things easier. So I'm going to focus here on this segment, and I'm going to use the right-hand rule again. So my thumb points towards I1, and I curl my fingers. And it's still going to point into your tablet or into the table. Assuming that your tablet is parallel to the table, it's on the table. The only difference is that the magnetic field here on this segment is going to probably be different, in value to the magnetic field here. And why is that? It's because of the radius in the equation. This guy, it changes. If you think about it, the radius here is 5 centimeters, but the radius here could be 6 from this wire to the loop. It can keep changing for these horizontal bits here. I'll do the same thing for this third segment now. Applying the right-hand rule again, my thumb points towards I1. It follows I1, so it's pointed parallel to our table, assuming we're sitting down and our tablet is flat on the table. Tablet, Android, whatever. And we use the right hand rule, we curl our fingers. And I still get that the magnetic field is pointed into the table, assuming our tablet or Android screen is flat on the table that we're using to study. I know I'm being redundant here, but it's just to explain things clearly. And now I focus on the fourth segment, where is the magnetic field pointing. It's also pointing into the tablet or into the table. Basically, we already know that our loop is sitting on the right hand side of this wire. So we already kind of know that it's going to point, as long as we're anywhere here in this space, as long as we're anywhere here in this space, the magnetic field will always point into the table. And that's what we've just realized. If the loop was here on the left hand side, then it would point out of the table or into your face or towards the sky. Now what I'll do is I'll find the force on this segment of the loop. It's going to be pointing towards the right because we're going to use the right hand rule. I'll probably erase a lot of these because they're getting a little messy now. We already know that for any point here, the magnetic field is always pointed into the table or into our screens, away from us, away from our eyes, in the negative k direction, assuming that we have y, x, and k is sort of pointed out like that. Z. Now I'll focus on finding the force on this segment of the wire. I know that the current is pointing down, so what that means is that my length vector here is in the negative j direction, okay? And I know that my magnetic field is from the first wire is pointed into the tablet, into the screen. So I'm just going to use the right hand rule. I'll start with my fingers following the current going straight down, and then I'll curl my fingers towards the magnetic field. So that's going to go into the screen again until my thumb points towards the right, once my hand turns into a fist, a closed up fist. So that my thumb will then give me the direction of the force on this segment of the loop. That's great. Now I'll do the same thing for this segment of the loop. And I'll have my fingers following the current, pointing upwards, pointing straight this way, parallel to the table. And my fingers will curl in the direction of the magnetic field, so they're going to go into the table or into the screen. And then my thumb is going to point left. So I'll call this the left-hand side, force on the left-hand side of the loop, and the force on the right-hand side. Now I'll focus on this segment. When I apply the right-hand rule, my thumb ends up pointing down. And if I apply the right-hand rule on this guy, this segment of the loop, my force points up. D for, I'll say B instead, B for the bottom of the loop. and U for the upper part of the loop, or I'll use T instead. So for the top of the loop, force on the top of the loop. Now, one thing I need to highlight here is these two forces actually cancel each other. And here's why. We know that Ft is always pointed in the minus J direction, and we know that Fb is always pointed in the positive J direction. Again, keep an eye on the coordinate axis I've given here. Now, when we look at this formula, and we try to apply it, if I focus on this one point here, and the same point down here on this other second segment, the forces will cancel each other. The only thing that we have to be careful about is that the magnetic field actually keeps changing. The magnetic field on this point, for example, is different than the magnetic field here. Why? Because of the R again. The radius keeps changing. So it's kind of like that's the radius for this point, and then this is the radius for that point. So the magnetic field keeps changing, but the fact that we have this length of wire, as long as as long as we have these two segments of wire, they'll sort of cancel each other anyways. That's the idea. So hence, again, because these two forces are pointing in opposite directions to each other, they'll always cancel. So we can let go of these two forces. And so the only two forces left are these guys. And they're not going to be the same in magnitude. Again, why? Because the magnetic field here and the magnetic field here are different because of the different radiuses from this wire. The distance from this wire to that point, and the distance from this wire to that point. Now I'll find, the first thing I'll do now is to sort of find the magnetic field, B1, the magnitude of the magnetic field, which is going to be 4 pi times 10 to the negative 7 Tesla meters per ampere. I'll probably make my writing a bit smaller. Times I1, which is 5 amperes, over 2 pi times R. Now, this is the tricky part, right? We have to find the radius of this magnetic field. So what I'll do is I'm going to try to find this force first, its value. So that means that I have to find the magnetic field right over here, the value of the magnetic field. So that tells me that the radius from this wire is 5 centimeters, or 0.05 meters if I convert it to meters. So I'll say BL instead. BL, magnetic field on the left hand side, and that's the magnetic field on the right hand side, which we'll use for the FR, that force. So that's 0.05 meters. I'll make it even smaller because I'm going to run out of space eventually. I'll plug this into the calculator. That's 2 times 10 to the negative 5 Tesla. But hold on. We also know the direction of the magnetic field. It's always pointed into the board, so it's negative 2 times 10 to the negative 5 in the k-hat direction, and that's in Tesla. Again, I have to decrease the size of this guy. There we are. Now I have to find the force on the left hand side of the loop, which is going to be the current in the loop times the length vector of this specific segment on the left hand side of the loop only, crossed with the vector BL. I know that the length vector, the current first, is going to be 1 ampere. And I know that the length vector of the segment here is going to be pointed downwards, always towards the direction of the current, so it's negative j hat. That's what I know for sure. And in general, we know that the length here is actually 20 centimeters, as they've told us here. So I'll convert that to meters. That is 0.2 meters. 0.2 meters in the negative j hat direction. That's our L2 vector, length of that specific segment of the loop, cross with BL, which we already have, negative 2 times 10 to the negative 5 k hat Tesla. Now force on the left hand side is going to be equal to, I'll do j cross k, negative j cross k, so that's going to be which is going to give us minus I negative I hat. That's awesome. And then I'll just multiply all the numbers together, so that's 1 times okay, now it was actually negative j cross negative k. That's different then. That's going to give us positive I hat, exactly, because yeah, we're pointing on the right hand side. So that's going to give us 4 times 10 to the negative 6 newtons in the I hat direction. Now I'm going to erase some of this stuff because it's way too messy. So we say bye to the magnetic field there. So that's one force. Now we find the magnetic field on the right hand side, so I'm going to solve for the FR. Essentially, I'll get there, but I have to get BR first. So that's going to be equal to 4 pi times 10 to the negative 7 Tesla meters per ampere. By the way, feel free to watch these videos on 2 times speed. Sometimes I do have the tendency to explain things a bit too redundantly. Is over 2 pi r. So now the radius is going to be different. We're looking for the magnetic field here, which means that the radius is going to be 5 centimeters and that 8 centimeters. So that's going to give us 5 plus 8 is 13 centimeters or 0.13 meters. That's the new radius. The magnetic field on the right hand side is going to be equal to, now I'm going to solve that's going to give us 7.69 times 10 to the power negative 6 Tesla And again, the magnetic field is pointed into the board, so it's in the negative k hat direction, or into your tablet if it's flat on the table, that is. So that's our magnetic field. And I'm going to erase these calculations now, because it makes things a million times easier. I'll erase that as well. And now I'm going to find the force on the right hand side. It's going to be equal to current in the second guy, instead of L2, I'll say LR crossed with B1, or BR instead, actually. So now our current in the second wire is 1 amperes, and we know that our length vector here is going to point always in the direction of the current. So on this segment of the wire, our current is pointed in the positive J direction. So it's positive J hat. And it's 20 centimeters in length, so I'm going to say 0.2 meters. You can convert to standard units always. SI units, sorry, that's what I meant. This crossed with BR, which is negative 7.69 times 10 to the negative 6 Tesla in the K hat direction. And that will give us positive J, and that's positive J, negative K, negative I hat, and the actual value is going to be .54, I'll round it up a bit, times 10 to the negative 6. That's going to be Tesla. So that's the force on the right hand side of the loop, pointing in the negative I hat direction. Now we're asked to find the net force on the loop. So the last step is simply to add these the force on the left hand side and the force on the right hand side. So when we add this guy right here, and this guy right here, we'll get a value of, sorry, I have to, okay, there we go, net force, which is equal to, they both point in the I hat direction, so we get 2.46 times 10 to the negative 6 newtons in the I hat direction. So overall the net force is pointed towards the right hand side. That was pretty much it, and again, feel free to watch my videos on 2x speed. I usually think while I solve the problem in the video. Take care.